Hey everyone, welcome to the recording for tutorial C3. So in this one we're going to be looking at digital circuits or logic circuits and see how they are made up. So basically digital circuits are based on Boolean algebra because that's what a digital circuit is, right? It's a bunch of ands and ors and nots and does various things when we put them together. So that's why when we talked about Boolean algebra in the previous week's tutorial, we looked at, how we can do a truth table for an algebraic expression to see what the output should be based on the inputs. So that way when you build it in as a digital circuit, you can then test your circuit because we know what the answers should be, right? And then we also looked at how to simplify an algebraic expression because you want your digital circuit to be in its most simplest form. So that way we don't waste any resources on the microchip for the circuit that we're building or however you're building your circuit. So how do we relate Boolean algebra to a digital circuit? Well, the first thing is how we represent the different operators in an algebraic expression. So we have the AND operator. So this is the symbol for the AND operator. So it looks like this one here. So there's two inputs, A and B goes into the AND. It does an AND operation, and then we get C as the output. The OR symbol looks like this on a digital circuit. So again, two inputs go in, it does an OR, and we get the output. And the inverter or the NOT operator looks like this symbol here. So you'll need to remember those symbols. This is a NAND operation or a NAND gate. So it does an AND and then a NOT straight after it. So it looks like this as in the algebraic expression, right? A dot B with a line over the top. So that's a NAND gate. So it does an AND and then a NOT. And this is a NOR gate. It does an OR and then it does a NOT. So that little circle represents the NOT after the OR operation. So using those, we can build up digital circuits, right? Now, we physically had physical breadboards in the tutorial to actually have a go at physically building them, just as a bit of fun. Now, we can't do that for the online students, obviously. Tim did post a link to this one, which was an online breadboard simulator, but I just couldn't get it to work for some reason. So you can try it, see if you can get it to work, but it doesn't seem to give me any extra wires. And if I click on it, it doesn't seem to do anything. I'm not too sure whether it's just my computer or what it is. I've tried it in Chrome and Firefox and it hasn't been no joy. So have a go at it. If you can't get it to work, it's not a huge thing because the physical breadboard aspect was just a bit of fun playing around with a physical breadboard. Now, if you are an on-campus student but you didn't make it to the tutorial, you can just during a lab session ask to borrow a breadboard and have a play around yourself. That's perfectly fine. So what we're going to do is we'll look at the second part for the, we're going to build this, but we're going to build it in Logisim, all right, and then have a look at kind of what it does, and that will give you an idea about what you need to do. Right, so that's down in the quiz preparation section, you need to use Logisim. So all the Logisim application is just a download from the 102 Moodle page. So if you go down to the download resources section, you'll see software used for concept quizzes. Just download that and unzip it. And where did I put it? No, it's in 102 University. So it's in the machine org. So it's the machine org zip file. So unzip that, then go into there, and then you'll find there was the binary that you had. So the one we want to use is Logisim. Now you may need to download and install Java. I had to do it on my computer, so you might need to do that. So if you double click on it, it'll tell you if you need to install Java or not. So double click on it, then we run it, and we get the Logisim environment. So up the top, we have things for, so this is a switch, this is a lamp, so we can get it to display whether the whole circuit is on or off. And then we have the NOT, the AND, and the OR gate, and we can just drop them on into our simulator here. All right, so let's just try connecting. So if we select that and then just drop it on, so that's our switch. And then let's do a light, drop that on, and then we want to connect them. So I think we use the little hand here, and that will allow us to, no, it's not that one, maybe it's this one. Yep, so that's the one we want. So you can see it allows us to draw a line between it. And then if we go simulate, so it's enabled. So that means as you turn the switch on or off, so go to the hand to be able to change the switch. So you can see now it's off, so the light is off. It's on, so the light is on. So you should do this with me in the tutorial. So pause the recording and maybe make sure you got that working on your one. All right, let's add a NOT gate to our simulation and test that. So we'll do that. Let's take our line. Can we unhook that somehow? No, so we might need to just hit the delete key. So select the wire and then hit the delete key on your keyboard and that will delete it. And then we connect it up to there. And then from there, we can connect it up to there. All right, so let's go to the hand, click 0, it does a NOT, becomes a 1, click 1, it does a NOT, it becomes a 0. So we can see that that is also working. All right, let's do an OR. So again, let's just delete these wires. Can you select multiple things? Oh, you can. So we can just select that, hit the delete. No, didn't select all of it. Select that, hit the delete key. Awesome. Or just shift the NOT up the top there. So let's grab an OR. Select that, drop it on. Even though it's got 3 inputs, we only need to use 2 of them, so that's fine. So we do need 2 switches though, so let's add another switch here. Let's move that up. And let's wire it together. Sweet. Go to the hand. So if they're both off, we get 0. If one of them is on, we get a 1. And if they're both on, we get a 1 as well. So that's working. Awesome. So let's select that. No, you have to go to the pointer, select our gate, hit the delete key. Let's replace it with an AND. I think it's connected the wires up as well, which is good. I go to the hand. So both off, we get 0. If one is on but the other is off, we still get a 0, and it's only when both are on we get a 1. So make sure your NOT, your OR, and your AND gate works correctly. All right, what we want to do now is build that circuit, which is this one here. So maybe pause the recording and you have a go at building that circuit yourself first. All right, so we need 2 NOT gates. Let's drop those on. Cool, we need 2 AND gates. Drop those on. Then we need an OR. Drop that on. And then finally we need our light. All right, so now we just need to wire it up. So let's say that this first switch is X, this one is Y. So X goes directly into the AND. So let's wire that. Cool. And then X goes into the second NOT. So I think we can branch off here. Go into that NOT. Cool. So let's do the Y. So Y goes directly into that second AND. You don't need to make that circuit look pretty or anything. Sweet. And then Y goes into the first NOT. If I do that, will it just jump over that other one? I think it will. I think it only connects to that wire if there's a dot there, so that's just going straight across. It's not connecting to this wire here. Sweet, and then the first NOT goes into the first AND. So that goes into there. And this not goes into that AND. So that goes into there. Oops, sorry, this one is incorrect. That one goes into, oh crap, I deleted the whole thing. Never mind, let's just drop the OR back in. You probably picked it up as I was doing it. So this goes into the AND, not the OR. Sweet, all right, so our two ANDs are now connected correctly. So the output of that goes into the OR. The output of this goes into the OR. Sweet, and then the output of the OR goes into the light. All right. So now you need to do it. So if you haven't built it, then build it yourself first. And then you need to test it and see what it does. So do a truth table for it and then come back to the recording. All right, the truth table is 0, 0 gives you 0. 1, 0 gives you 1. 0, 1 gives you 1. And 1, 1 gives you 0. So do you know what type of operator this is? This is the exclusive OR, right? So for exclusive OR, you only get a 1 if one of the inputs is a 1 and the other is a 0. If they're either 0, 0 or 1, 1, then you get a 0. The exclusive OR is actually really important. So this is how we implement the exclusive OR as a digital circuit. Now it's really important because it allows us to add two bits together, right? 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, but we carry 1 across, all right? So we need to be able to have the result, but we also need to be able to have a carry. So to do that, we extend our circuit to add this part of the circuit. So this is what's called a half adder, which allows us to have a result and a carry. So let's add this extra part in. Or actually, why don't you pause the recording and why don't you add that into your circuit. All right, so we'll add this in. So again, basically the two switches go directly into this AND. So let's just pull a wire from here. And then pull a wire from here. And we need another light. Awesome. All right, so pause the recording, have a go at the truth table now. Right, 0, 0 gives us a result of 0, carry of 0. 1 plus 0 is 1 with no carry. 0 plus 1 is 1 with no carry. But 1 plus 1 gives us 0, and 1 is carried across. Okay, so there we go. There's our full half adder circuit. So it might be useful to save that. So just go File, Save As, and save your circuit somewhere, so that way you can load it back up again. All right, so the half adder still doesn't allow us to fully add two bits together because you need to allow for adding two bits and a carry, right? And for one particular set of bits. So what we need to do is, we've done this part, we need to make a component out of that, and you can read through the instructions on how to do that. And what you need to do is chain two half adders together. So the first half adder adds the two input bits, so A and B. The result of that goes into another half adder, and the other input of this half adder is the carry from the previous operation. And then that gives us the result plus a carry, and it does an OR between the carry of the first one and the carry of this one here. All right, so by doing that, that gives us then a full adder. And so if you make that a component, to be able to add two 4-bit binary numbers, we have to chain two full adders together. So A0, B0 is the very first bits on the right-hand side of your binary number. Then it's A1, B1, A2, B2, A3, B3. So you can see that the carry from this one feeds into the input of the next operation. Then the carry of this one feeds into the input of that one, and the carry of that one feeds into the input of that one, and so on. Now you'll notice that the very first full adder here has the carry for that is just logic 0. The reason being is that there's no operation before it, right? So that way, for the very first operation, the carry must be 0 because there's no operation before it. Sweet. So what you need to do is basically we've done this part. So we've built the half adder. So you need to follow through the rest of the instructions to build a full adder and then show it adding two 4-bit binary numbers together. All right, so that's the basics of a digital circuit. And by using logic simulators, it makes it much easier for us to design circuits and so on. Whereas in the early days, when we didn't have computers, when they were first building the computers, you had to build the circuits by hand. And I can actually show you a picture of that. If we just go to Mr. Google here and let's search up ENIAC, which was one of the very first electronic computers. Let's look for some images. And here's a cool image here. Let's bring that up. You can read through the first digital computer. So basically, these lovely ladies here were actually programming the ENIAC computer. So it's got a bunch of valves and things for storage, and then it has a bunch of switches and outputs and logic gates and stuff. And to program it, you had to plug the wires into the correct holes there. So you can imagine something was slightly wrong, and trying to debug that would be absolutely insane, right? So kudos to those people. So these two women here were two of the first ENIAC programmers. And in fact, the very first programmer was Countess Ada Lovelace, who made the Charles Babbage's analytical engine calculator do something different. So basically, women were the mothers of computer science, if you can say that, which I probably do. All right, that's it for this tutorial. I will catch you in the next one. Bye.